Question number 1.15. An elevator car whose floor to ceiling distance is equal to 2.7 meters. An elevator car distance is equal to 2.7 meters. 2.7 meters. Starts ascending with constant acceleration 1.2 meters per second square. Full stop. 2 seconds of 1.2 meters per second square. Okay. Full stop. Okay. 2 seconds after the start, a bolt begins falling from the ceiling of the car. 2 seconds after the start, a bolt begins falling from the ceiling of the car. Find A, the bolt's free fall time. The bolt's free fall time. B, the displacement and the distance covered by the bolt during the free fall. In the reference frame fixed to the shaft of the elevator. In the reference frame fixed to the shaft of the elevator. That means outside the elevator. I mean, the reference frame is on the earth. Okay. Yeah. So, did you write down? Okay. So, try to solve this problem. Here, only thing is now, till now we were solving all things where there is velocity which is constant. All of them. Here, one of them is getting accelerated. So, it is no more a very simple inertial frame. But you can think and try to solve this. Okay, spend some time on this. I want you to spend at least an hour trying to solve this. Doesn't matter whether you solve or not. Okay. So it is important that you spend time and find at least on 5 or at least some 10 pages I want you to scratch. Okay. So last class, whatever problem I gave, did you try at least? Okay. So shall we start now? Because it will get delayed otherwise. Okay, we will start with how to do this problem. Okay, so it is important to visualize the problem. Otherwise, what happens is you will tend to make mistakes in the assumptions. Okay. So let's start with the problem. What is the problem? There is this elevator. So I'll just write the elevator here. Okay. And this elevator is in the ground floor, assume first. Okay. And we were told that elevator height is how much? Okay, this is 2.7 meters. Okay, and then it actually starts going up with an acceleration of 1.2 meter per second square. So let's say after about 2 seconds, that's what is being told. So after 2 seconds, it would have traveled some distance. Okay, so at that time, assume that it is somewhere here. Okay, I will just write it like this. Okay, so after about 2 seconds, it is somewhere here. Okay, so how much, where it is, we can easily find out. Okay, that is a normal formula we can use, and we can find out. That is not a problem. Okay, so let us say it is here, and at that time, what happens? On from the top, okay, there may be some light here, and it has some nut and bolt, and that bolt actually drops from there. There is some bolt here, which will drop from here. Okay, so when it drops, the question basically asks this. You look at this. When it drops, what will happen? Okay, first we will see what will happen. Okay, so when it drops, very clearly, it had already acquired certain velocity. Okay, it has some velocity. Assume that for a second, assume that there is no gravitation. Okay, when it just detaches itself from the lift, if there is no gravitation, okay, what will happen to this? So it will keep going upwards, okay, with some velocity. What is that velocity? We can always calculate. Okay, so it is the velocity at which at the point at which it has detached, whatever was the lift velocity. At that velocity, it will start keep going up. If there was no gravitational force, even then, okay, even then, if you carefully watch, even then actually, the lift actually is going up much faster because it accelerates. Okay, and when it accelerates, this is going. Sorry, look at this. The bolt is going up, the lift is going up. Okay, but actually, if you are inside the lift, what do you see? No, first of all, you see that bolt actually falls to the ground. Because what is happening? Bolt is going in this direction. Look at this. Bolt is going in this direction. Lift also is going in this direction. It is just that lift is going faster, and it is acquiring more and more velocities as it progresses because it is accelerating. Whereas the lift is going at a certain constant velocity, and because of that, a person who is standing inside the lift will see that the bolt will come and hit the floor. And if somebody asks you a question, how long it will take to hit the floor, you should be able to find out. There is no gravitation. So only thing you need to find out is this. See how much this bolt is going in this direction. Okay, and this guy is going in the same direction, but there is a difference. This is accelerating continuously. So this problem, first you just try. One minute you try this. Okay, if the bolt is continuing to go with the same velocity, what is that velocity? We'll figure out that velocity first. Okay, that velocity v, let us say bolt velocity, initial velocity. Okay, I will call it as v naught. Okay, v naught is actually is equal to u plus at, which is the velocity of the lift at that point of the detachment. And u is the velocity of the lift at the beginning, and t is the time taken for that, and a is 1.2 meter per second square. How much velocity the lift has gained by the time it has reached that height? That much we can actually calculate here. 0 plus 1.2 into t is the 2, okay, which is 2.4 meters per second. That is the velocity with which the bolt is going. Okay. Now, we can clearly say at this point of time actually by using relative velocity, okay, at that point of time the relative velocity of lift with respect to the bolt is actually 0 at that exact instant when it detached. Because lift also is at 2.4 meter per second and bolt also is 2.4 meter per second. Relative velocity is 0. Okay, we can take that velocity as the starting point for us. 0 we will call it. So we will consider everything with respect to that frame of reference. Okay, that frame of reference is what? One which is going at 2.4 meter per second square. That is the frame on which we will stand. Okay, let us say we will have a frame here. At this instant, I will write x and y axis. X and y axis. Okay, and this is my frame of reference I will actually work with. And this frame actually is moving in this direction with 2.4 meter per second. Okay. With respect to this, you can be very clear that the bolt actually is stationary. Do you agree? My question is, I am going to take a frame of reference, okay, which is actually also moving at 2.4 meter per second square per second, constant velocity. Okay, if I see from this frame, the bolt is always stationary. Correct? Now we can always say bolt is stationary and this fellow lift is moving at 1.2 meter per second square with initial velocity of 0. Correct? Now for it to hit the ground, actually it doesn't hit the ground. It stays there and the ground hits that. It doesn't matter. Okay. So it actually, as far as we are concerned, the total distance of 2.7 meters to travel, okay, how much the lift took, that you calculate first. So, and that would tell us basically how much time it takes for it to hit the ground. Did you understand? Okay. Now calculate quickly and tell me how much it is. So T is equal to square root of 5.4 by 1.2. 4 point? I don't think that is correct. How much? That is 4.5 is T square, correct. So what is T? Square root of 4.5, which is? Okay, this is fine. This is actually, what did we calculate? Correct. If there is no gravitation, how much time it takes to come up? Come up in the sense go down from the frame of reference of this. Okay. Now, if there is gravitation, okay, then the time that you are going to calculate here, will it be more or less? Then it has to, now there is a pulling force downwards, now it has to come faster than this. So how much do you get, how much will you think it will take? So how do you calculate this? If there is gravitation. So it is quite an interesting thing. See how to handle such kind of a scenario. Okay, now if you have, let us say one box. That box, if it is actually going up with certain acceleration, okay, in this case it is going at 1.2, okay, and there is something inside, okay, whose acceleration is 9.8. downwards. Okay. Now that actually means if you keep the box stationary like this, if I go into the frame of reference of the box itself or the elevator itself, how fast it will be falling with respect to that. So carefully look at it. What I am doing is that actually this box is going at 1.2 meter per second square. And the ball inside this is coming down at 9.8 per meter per second square, coming down. Okay. Now, if this is not moving anywhere, then this 9.8 is 9.8 only. If it is going up at 1.2 meter per second square, what would be the ball's acceleration with respect to the box? So let's look at it. Now let me ask another question. Okay, now this question will clarify clearly. Okay. So this box is there. Now wait, just box is there here. Now instead of box going at 1.2 meter per second square, let us say box is going down at 9.8 per meter per second square. And when you are standing inside here, okay, what do you see the ball as? Stationary, correct? That means ball is not at all going anywhere. Okay, stationary. But it is not 100% correct what you are saying. Okay, let us say a ball was actually moving at certain velocity earlier. Okay, then you will see that the ball is actually moving at the same constant velocity, whatever it was. So initial velocity, if it had something, if it had some initial velocity, think about it. If the ball had some initial velocity, what would happen? So what I am saying basically is that if both of them are actually at the same acceleration downwards, that cancels out for you. Okay. So if this is 9.8 and if this is just 5, or let us say this is a downward acceleration of let us say 8.8. Okay. Then you will see that this ball is coming down slowly. Do you agree? Because this is going downwards and this also is going downwards with an acceleration, and both of them basically kind of here subtracts. Okay, so 9.8 minus 8.8, about 1 meter per second square with which this is coming down. On the other hand, if this guy is going up, like how we talked about, with 1.2 meter per second square, so what is the effective acceleration of this guy? So this is 9.8 plus 1.2, 11 meter per second square. So you imagine like that when you are thinking. Now you put it both equal and see which direction you have to subtract, which direction you have to add. Otherwise you will get confused. Okay. So it is basically 11. See, if it is standing still, it is simply, if you take in the reference of, if you are standing in the reference of the elevator itself, okay, inside the elevator you stand. With that reference, if you see everything, then this bolt is actually coming down at an acceleration of 11 meters per second. What is the acceleration of the bolt with respect to the frame of the elevator? I am making you think a lot in terms of relative velocities. Now you have to simply calculate for 11 meters per second square acceleration, if it comes down instead of 9.8, how much time it takes to basically come from top to the bottom. 2.5 meters. So just find out now. Only acceleration is now to be taken as, so S is equal to ut plus half at square. To travel, how much? 2.7 meters. Okay, this is 0 because both of them at that instant basically had exactly same velocity. Okay, plus half into 1.2 into how much? T square. Okay, so T is equal to, comes as 0. Correct? So it's actually 0.49, square root of 0.49 will come as 0.7 seconds. Now this is actually strictly speaking quite a straightforward answer actually. If you understand basically how is the frame of reference works in an accelerated frame, okay, this is quite a straightforward answer. Okay. Now we have to find, this is the A part. Okay. Now what is the B part? So now you look at how this bolt actually goes from the frame of reference of the shaft. Shaft in the sense that it is a fixed frame of reference. Okay. The shift. This is basically our frame of reference. We are standing here. That is the shaft. Okay. So from its frame of reference, if you see, what is the distance and the displacement of the bolt? Now I am going to tell you how the bolt actually moves. Okay. Now you tell me whether you agree with or not. Okay. In my view, bolt actually, initially when you drop, initially it goes up from the fixed reference outside. Okay. Initially it goes up because it is having a already certain velocity. Okay. So it goes up, it is like ball thrown up. It goes up for some distance. Okay. Like this. Okay. And then it comes down again and goes down below that, and at some point by then the lift would have moved to some distance and it will hit the floor. It actually does. If I write it in a big way, from here it was there, it went up like this and came back like this, and by then lift floor would have come here. This is how it actually goes. It goes up, comes down and hits the floor. Do you agree with this? See, the bolt, see, I am taking first of all, this is my lift top part, okay, and the bolt is somewhere here. Now the moment it gets detached, it already had acquired certain velocity. Okay, after 2 seconds only it gets detached. So it is like saying that I take my hand up like this fast and leave the ball here. Exactly like that. Okay, you take it like this and leave it like this. So then what happens? Ball will not suddenly drop. It will go up and then come back. Okay, it will go up as long in the sense that initial velocity is the velocity at which you left it, and then gravitation acts on that. So it keeps slowing down, peaks at 0 and start coming down again. Okay, and it reaches the point at which it was first thrown from, and then comes down again, and finally reaches the bottom of the lift, because lift now would have moved up here because it is already going up. Okay, so now whenever they say you have to find the displacement, we have to find this one. Okay, and when you want to say distance, that is this plus this plus this. That is the distance and that is the displacement. Did you get this? Okay, now see whether you can do this. So you have to calculate the distance and the displacement. Displacement is actually very straightforward. So you know what is its acceleration. Now when it is, see, what is the force acting on it? Only gravitation is acting on it. So now for a minute, now you forget everything. Okay. So you think about only one thing, which is the bolt. Okay. Think about what is its initial velocity, what is its acceleration, all that. So you will get to know the idea. What all things we know about the bolt? Initial velocity is how much? 2.4 meter per second, correct? Okay. So final velocity we don't know, because I am talking about the whole path, full path. Okay. So final velocity when it hits here, what is it? We don't know. Okay. So that we don't know. So however, we know one more thing. Okay. So in both cases, what is the acceleration? So because remember this, at that time we took the acceleration of the bolt with respect to the reference frame of the elevator. Now, and we said that it is 11. Now we are actually standing outside and just looking at the bolt. We don't care about the elevator. So what is its acceleration now? Correct. Minus 9.8 meter per second square. No, if you take the direction of u as positive, which is in the upward direction, so any one you take it as one positive and everything else has to calculate with respect to that. So if u is in this direction, if a is in this direction, then a has to be negative. Otherwise, if you take u as negative, then a is positive. Okay. So they are opposite. So a we know. And we know one more very interesting thing. What is that? We already calculated the time of flight. How much? So we know that t, total time t for it to hit the ground is 0.7 seconds. Okay. Now what is left for you to calculate? Yes. So see how the problem becomes extremely simple. See, when you get confused, you have to remove things out of your head and only concentrate on what you exactly want. And what data you have, what you want to find out. S is equal to ut plus half at square. That's all formula, no? Apply formula and calculate. Nothing else. No, let's do it actually. Okay. So 2.4 into 0.7 plus half into 9.8 into minus 9.8 actually, okay, into 0.7 square. Okay, so I'm going to take 0.7 common here and just write here 2.4. See, now please watch basically when I'm doing arithmetic, because it is important to be able to do arithmetic very fast in your competitive examinations. Okay, so just watch basically how to do simple arithmetic. 0.7 you take it out, put 2.4 plus 9.8 divided by 2. Divided by 2 is 4, how much? 4.9. Okay, 4.9 into 0.7. Correct? Is it correct? So this is actually how much? Correct. It's almost basically 3.4. Okay. 2.4 minus, let us say 3.4 approximately. Okay. So this is nothing but 0.7 into minus 1, which is minus 0.7 meters. A little bit of 0.7 something. Okay. Okay. So why is it minus? Because we have taken going upward as positive. So this is coming downwards, so it is 0.7 meters, minus 0.7 meters. So now that you have calculated the displacement, how will you calculate the distance traveled? Look at this. Okay, this plus this into 2. Okay, so you can calculate how much time it takes to velocity to become 0. Okay, with this acceleration and initial velocity 2.4. So that into 2 will be this, plus this is the distance. So quickly do it and tell me. This we have already calculated to be 0.7. Now if you calculate this going up, that into 2 plus 0.7 is total distance. So you have u how much? Okay, v0. A how much? Okay, yes, we don't have. We don't know how much. So we just have to find out yes. Okay. So what formula are you going to use? That formula. From that formula you calculate now. How much? Correct. That's approximately 0.3. Correct. Okay, negative 0.3. It's not negative actually. Sorry. This is 9.8. I take it this way. This will become positive. No? So it is not negative. So 0.3. So going up is 0.3. Coming back is 0.3. Total distance is equal to 0.3 into 2 plus 0.7. So 0.6 plus 0.7 is 1.3 meters. The point basically is this: when I explain the problem, you will be able to do it. You will be able to understand. The question is, when problem you have to do, okay, you have to do on your own. At that time, you will get into several problems, okay, and that will happen for some more time, okay, till we do even little more problem. Because until you try these complex problems, that thinking will not come. So it is important that at all the times you think and try to find answers by yourself. And if that doesn't happen, I will help you. But one day when you solve the IRODOV problems on your own, then you will not turn back. You will be able to solve many more problems like that. Okay.